Hello, class. So today we are going to talk about some different aspects of measurement, and here we're going to talk about different ways that we can look at or express errors in measurements. And so the two most common terms that we associate with error or looking at error in measurements are what are called the accuracy and the precision. So let's just first define these. So accuracy refers to how close the measured value is to the actual value or the true value. Right? So in order to know if we're accurate, of course, we have to actually know what the true value is. Right? And then we can judge how close our measured value is to our actual value. So an individual measurement can be either accurate or not accurate, depending on how close it is. Now, oftentimes to improve the accuracy, right, we'll repeat a measurement and we'll look at how accurate the average value is. Now, precision, on the other hand, refers to how close a series of measurements are to one another. So first of all, right, we have to have multiple measurements to look at precision, right? Because it is looking at how, if we do a set of measurements, how close those measurements are to each other. Another way that we sometimes will refer to this is how reproducible a measurement is. So if we do it, 3 or 4 times, how close are those numbers to each other? Now, precision has no reference to the true value, right? So we can have great precision and not be anywhere close to the actual value, right? And we'll talk about that in a few minutes. So, accuracy versus precision. So we want to make sure that we understand the differences between those and not just use them interchangeably. Right? So accuracy, how close you are to a target value or to the actual value, and precision, how reproducible a series of measurements are. In other words, how close they are to each other. So let's look at a set of data and just analyze it for precision and accuracy. So if we look at this first set of numbers, student A, right, and we did 4 measurements, and we see here that the true value is 10 grams. So in terms of looking at accuracy, we're going to look at the average. So the average here is not awful, but it's maybe not what we would call accurate, depending on how we're doing these measurements. But it's not terribly close to the 10, right? And if we look at these values, we can see there's a whole lot of scatter, right? They are not terribly close to each other, right? So this set of data is not very good at all, right? It's not very accurate, and it's not very precise. So this is sometimes referred to as we have scattered data, right? Now, if you look at student B, we look at the average here, it's again not terribly close, even further away than last time. So we would clearly say it's inaccurate. But if you look at the numbers, they're really close to each other, right? So these values are terribly precise, but they're not very accurate, right? So this is that example where the numbers can look good, right? In other words, we can keep getting the same number over and over again, but it's not close to the actual value. So it's precise but inaccurate. And then finally, student C here, we have an average that's very close to the true value, so it's very accurate, and we can see all the numbers are pretty close to one another, and so we have, sort of the ideal data, which is both accurate and precise. So, what's going on here? Why are these numbers sort of off? Well, if we look at student A here, right, clearly this is sort of scattered data. So oftentimes in lab when we see this kind of data, right, we think about people not being terribly careful, or maybe not following the procedure correctly, or not, being really careful about their measurements, if they're measuring out different values, right? But, and we can see sometimes we're too high, sometimes we're too low. But one thing that we can see is that because sometimes we're too high, sometimes we're too low, that if we do enough of these measurements, we can see that our average is actually not awful, right? Even though this one is really high and this one is really low, and this one's pretty close, but we can average these out. So this is being caused by what, we'll flip over to the next slide here, by what we refer to as random error, right? So this is an error that has equal probability of being too high or too low. Right? And the nice thing about this is random error will typically average out with enough trials. Okay. So the situation in student 1, student A might be a situation where we're getting some sort of random error in the data. Now, this is like student B, right? Now notice here the error is always the same. It's always too low. So this is what we refer to as a systematic error, right? Meaning we're reproducibly getting the same error. Now, the good thing about systematic errors is oftentimes we can find the root cause of systematic errors. Maybe there's a miscalibration in the instrument or something that's always causing us to have the same kind of error. Now, the bad part is they won't average out, right? So if we don't recognize it, doesn't matter how many trials we do, that error is always going to be there. Now, the opposite was true for random error, right? It will average out, but it's pretty difficult oftentimes to figure out the source of random error because sometimes it's too high, sometimes it's too low, so it's probably different things that are causing the error, and it's just, maybe a multiple of errors going on, this error in this trial and this different error in this trial and so forth. So, systematic error. So systematic error is an error that is always too high or too low. And this will not average out. So, error is inevitable, right? This is the thing why we have to worry about error is that, error is going to be inherent. And so it's a matter of recognizing the error and trying to minimize them. Now, when we do lab, we often will do some basic calculations to try to estimate an error. So, for example, one thing that we will do to try to look at, say, the level of accuracy that we have is to do something that we call a percent error. So the percent error calculation, and you'll do this in lab quite often, is simply the experimental value minus the accepted value, or the true value, and depending on, how you're doing, if you look this up, sometimes this will be an absolute value, sometimes it's not. It sort of depends on whether you want to know the absolute error, meaning just how much it's off by, or if you also want to know whether that error is too high or too low. So it's the experimental minus the accepted divided by the accepted times 100. And this error is meant to give you sort of an idea of the accuracy, right? So how far in terms of percent are you off from the true value? Now, percent errors are great. They can be sometimes a little troublesome if you have really small values, meaning if your true value is really small, because then even a tiny error is going to result in a large percent error. And so percent errors can be sometimes misleading, but if we understand sort of the idea going in, then we can sort of understand that, if we have a really small accepted value, even a small error is going to be a large percentage of that expected value. Now, we'll do this quite often. Another way that sometimes we can assess error is what's called a standard deviation. This is a little bit more complex calculation. I'll give it to you in lab when you're called upon to do it. But essentially, this is a way to look at precision of the data, right? So how far, in other words, it's sort of giving you an idea of how far, if you have multiple measurements, right, how far is actually each measurement off from the average measurement, right? So if you take a bunch of numbers, a bunch of measurements, you get the average, and that's what you report. So the standard deviation gives you an idea of the scatter in your data. So how far away each value is, or how far away the values are from each other. So it gives you an idea of how much precision you have in your data. So a small standard deviation means you have more precise data. Bigger standard deviation means there's more scatter. There's more spread in your numbers. So these are some ways that we will, especially in lab, look at the error in our measurements.